Hey team, we're back, week 4. This week we only have one section and we are done with Unit 5. So once you're done with these notes, you are ready for the review and the test. So let's get to it. We are going to talk about substitution in definite integrals. So last week we talked about substitution and how you can plug in the u and the du. But those were with indefinite integrals where we didn't have the limits on our integrals. So this week we're going to talk about what happens if we have those limits. How do we deal with that? And we actually have two options. So on this first problem, we're going to go through both ways that you can go about dealing with that, and you can kind of choose which way works. And then we're going to talk about some area between curves. Last week we talked about area under the curve. This week, we're going to talk about area between curves, and then that's it for Unit 5. So when we have substitution in definite integrals, we have a fun fact. You have your limits, a to b, of f of g of x times the derivative of g of x. So you can substitute your a and b into that g of x equation, and then just do your u substitution and plug that into f. So that is the way that we're going to usually do these problems. So because I know that made perfect sense, let's do an example. So I'm going to evaluate from -1 to 1 the integral of 3x squared times the square root of x cubed plus 1 dx. So I start with finding u. That's always my inside function. So u is going to be x cubed plus 1. We find the derivative of that for du. So the derivative of x cubed is 3x squared, and then the derivative of 1 is 0. So u is x cubed plus 1. Du is 3x squared, which is nicely already in our problem for us. So what we're going to do is plug these in to our u. So when x is -1, u would be -1 cubed plus 1, which would be -1 plus 1 is 0. And then we go to the top number, 1. When x is 1, u would be 1 cubed plus 1, which is 2. So now we're going to rewrite our integral and say, okay, this original problem would be the same thing as the integral from, instead of -1 to 1, now it's going to be 0 to 2, of the square root of u, which I'm going to write as u to the 1/2, and then that 3x squared dx turns into du. And now I just need to solve this and I'm done. So u to the 1/2, add 1, that would be 3/2, over 3/2 would be a 2/3 out front, from 0 to 2. I plug in 2, and I get 2 to the 3/2 minus 0 to the 3/2 when I plug in 0. Well, 0 to the 3/2 is just 0. So that's just 2/3 times 2 to the 3/2, which really means the square root of 2 to the 3rd power, which is 2 square roots of 2. And then I multiply 2 times 2 square roots of 2, and I get 4 square roots of 2 all over 3. And that's it. That's my answer. I'm done. I told you I would show you two ways, though. So what's the other way to do this? The other way is just to take your problem. So right here, where I had 2/3 u to the 3/2, not to change that 0 to 2, and to plug my u back in. So right here, where I have that 2/3 u to the 3/2, replace your u with x cubed plus 1, and then plug in your 1 and your -1. So if you do that, you plug in your 1, you plug in your -1, you simplify, and you still get the same answer. This is the way we typically use, but you could also do it that way if you like that way better. Whatever makes you happy. So let's try a couple more. Make sure that you're feeling comfortable. Letter A. We have the integral from pi over 4 to pi over 2 of cotangent theta cosecant squared theta d theta. So when you're deciding what your u should be, remember what the antiderivative and the derivative are. I know the derivative of cotangent is cosecant squared. So if I make cotangent my u, my derivative is the rest of this just with a negative. So all I have to do is put a negative on that. So now I'm going to say, okay, when theta is pi over 4, I plug a pi over 4 in for u. Cotangent of pi over 4 is 1. Okay, when theta is pi over 2 up top, the cotangent of pi over 2 is 0. So now I have the antiderivative from 1 to 0 of u times negative du. Well, I can move that negative to the front, and the antiderivative of u is u squared over 2. So I have negative u squared over 2 from 1 to 0. And you always do top minus bottom. So even though those are in opposite order, the big one's on the bottom, that's okay. It'll work out once we plug our numbers in. So I plug in 0. That's 0, right? Minus, I plug in 1, and I get negative 1/2. So that's gone. I get negative 1/2, which is positive 1/2. Letter B over here, tangent x dx. That's tough because I don't have, if I say u is tangent of x, I can't really do that. So instead, I'm going to change tangent to sine over cosine. Because then I could say, okay, well, if u is cosine, du is negative sine. That's not so bad. I just need to add a negative in then. So, okay, let's say, okay, when x is negative pi over 4, then u would be cosine of negative pi over 4, which is square root of 2 over 2. If I plug in positive pi over 4 to cosine, then I get u is square root of 2 over 2. So if I plug in my u and all that, I get a negative integral from square root of 2 over 2 to square root of 2 over 2 of 1 over u du. So, okay, that seems like it's not going to be the prettiest integral, but think of my limits here. I'm going from one thing to the same thing. And we talked about limit laws if we have the same limits, or you can just think about when I work this out, when I plug in the same thing, they're going to cancel each other out when I subtract. Either way, I'm going to get a 0. So if you get the same things, you don't have to do any work. Cool. Perf. So that's how your substitution with definite integrals works. A fun fact. If f and g are continuous with f of x greater than or equal to g of x throughout an interval ab, then the area of the region between the curves f of x and g of x from a to b is the integral of f minus g from a to b. Looks like this. The area is the integral from a to b of f of x minus g of x. So, fun fact down here, the graphs of f and g, which you can graph on your calculator or on Desmos, usually will clearly show which one is greater, if your f of x or your g of x is greater, because you always want to do the greater minus the smaller. The greater one is the one on top. So you want to do the one on top minus the one on the bottom. What does that mean? Let's do a couple examples. Find the area of the region enclosed by the parabola y equals 2 minus x squared and the line y equals negative x. Last week we talked about the area under a curve to the x-axis. Well, now we might go below the x-axis. It just depends on what we're finding. So same thing applies as last week. First, we need to find our limits of integration, but we're going to find them by just setting those two equations equal to each other. We just want to see where do they meet. So if I do 2 minus x squared equals negative x, I need to solve that. So I'm going to add over the x, or since I usually want a positive x squared, I'm going to subtract the 2 and add the x squared. So now I have x squared minus x minus 2. So I want to factor that. Factors of -2 that make -1 would be -2, +1. Set your factors equal to 0 and solve, and you get 2 and -1. So I know I'm going to integrate from -1 to 2. But I want to integrate the big one minus the small one, but which one is bigger? So this is where you graph your equations. So if I graph those, I graph these in Desmos, and I did an extra special graph for you so you could see exactly what we're doing. So obviously the parabola is my 2 minus x squared. The line is my -x. And then there's my x equals -1. Down here is my x equals 2. And I'm finding all of that purple area. I'm finding the area of that purple region. So your area might be a nice number, it might not. That's why we have to do the integration. So I can see here that this whole distance, okay, from -1 all the way to 2, my parabola is on top. So I can say 2 minus x squared is the greater, the upper function. So I'm going to integrate from -1 to 2, my upper function, 2 minus x squared, minus my lower function, -x dx. Let's clean that up a little bit. Distribute that negative. I like to put things in order, so I'm going to put -x squared first, positive x next, and then that plus 2 dx. When we integrate, -x squared is going to become -x cubed over 3. Positive x is going to become positive x squared over 2. And that plus 2 is going to become plus 2x. We're still integrating from -1 to 2. So we're going to plug in 2 for all of those x's, minus we're going to plug in -1 for all of those x's. Simplify that down. This whole thing becomes 10/3. This whole thing becomes -7/6. When we subtract, we're really going to add, and we get 9/2. So the area of that purple region is 9/2 or 4.5. So that's how that works. We're going to do one last example. Got a random fun fact there. Find the area of the region in the first quadrant that is bounded above by y equals square root of x and below the x-axis, below by the x-axis, because it's in the first quadrant, and the line y equals x minus 2. So let's graph that and make sure we know what's going on. So the red graph here is y equals square root of x. And then we have the line y equals x minus 2, like that. And since we just want the first quadrant, we have it's bounded below by the x-axis right in here. So I need to make sure that I know the bounds. So I'm going to set square root of x equal to x minus 2. I want to solve for x, so I'm going to square both sides. That gives me x equals, we got to FOIL that out, x squared minus 4x plus 4. Subtract that x over. Factors of 4 that make -5 would be -4 and -1. Set those equal to 0. We get 4 and 1. But anytime we square both sides, we've created another factor of x that wasn't there to begin with. If I plug in 1, I get square root of 1 equals 1 minus 2. That's not true. There's no graph over here at -1, right? So 1 doesn't work. My only answer is 4. And I can see here at 4, they definitely meet. So I'm feeling good about 4. The problem is when I look at this graph, when I go from 0 to 2, square root of x is definitely my top graph, but the bottom graph is the x-axis. So my subtraction of f minus g is going to be the square root of x minus the x-axis is y equals 0. So square root of x minus 0, which simplifies to be square root of x. From 2 to 4, my top graph is still square root of x, but now my bottom graph is that blue line, which is x minus 2. So f minus g is square root of x minus x minus 2. Distribute your negative. So that simplifies to be square root of x minus x plus 2. So we have to do two separate integrals here. One for this first chunk where the x-axis is the bottom, and one for this second chunk where x minus 2 is the bottom. So my area is the integral from 0 to 2 of square root of x dx plus, because we're going to add those two areas together, the integral from 2 to 4 of square root of x minus x plus 2. So if I find the integral of square root of x, that's like x to the 1/2. 1/2 plus 1 is 3/2. And then if I put it over 3/2, skip, flip, and multiply, that's 2/3 out front. We're integrating that from 0 to 2. Plus, we just integrated square root of x, got 2/3 x to the 3/2. Minus the integral of x is x squared over 2, plus the integral of 2 is 2x, and that we're integrating from 2 to 4. So let's talk about this one. If I plug in 0, it's not going to matter. So I plug in 2. This guy, I've got to plug in 4 for all those x's, and then I've got to subtract and plug in 2 for all those x's. Whew. So my first part, I get 4 square roots of 2. My second part, where I plug in the 4. And then my third part, where I plug in the 2, I get some cool stuff to cancel out. My 8's cancel, my 4 square roots of 2 cancel, and I end up with 16/3 minus 2 plus 4 gives me 10/3. So the area of this chunk right here is 10/3. Whew! That's it. Done. So now that we've gone through those, you can do week 4 homework. It's fairly short. It's just over those notes we just did. You can look over the Unit 5 review, and you can take your Unit 5 test. Make sure you send me your work. And all we have left is 3 sections for Unit 6 to do over the next few weeks. So we're on the downhill slide. You guys are doing awesome. Make sure you let me know if you have any questions. Email me. Let me know if you need a Zoom session. Whatever you need, I am here for you.